Hi guys, this is a video on section 1.6 from your book, which is called Continuity, and you guys have a pretty good background on a lot of this material from last year, so it shouldn't be too difficult. The one major change is that we're going to have a formal definition for continuity as opposed to just kind of a layman's definition that we used last year. So I want you, just like you've done in the past for me, to take notes on this. Write down any questions that you might have so that when I see you again, we'll be able to talk about any questions or confusions that you might have. So to start off with, we're going to kind of revisit continuity the way that we looked at it last year. And just by what we consider to be a layman's definition, to say that a function is continuous, so this is what our focus is here, means that there is no interruption, which would constitute a gap, a jump, or a hole in the graph at a specific value that we're going to call C. We looked at continuity last year when we dealt with rational functions, and you were showing me and telling me where the breaks in the graphs were. And that's a lot of what we're going to do here, but we're going to, like I said a little bit earlier, we're going to lead into a more formal definition that has to do with the calculus that we've been studying. So I'm going to move over to the next screen so that we can define it a little bit better. And we're going to first of all look at this graphically. So I'm going to draw you a couple graphs here so that you get an idea of what's actually going on. The first is going to be that of a continuous graph, and it's going to look something like this. We'll draw what looks to be like a first coordinate or a first quadrant coordinate plane, and I have an x and a y axis, positive x and a y axis, and on that coordinate plane I'm going to graph something that looks like this. I'm going to have two open dots, and that's going to be my graph. Not great here with the Screencast-O-Matic and the stylus as far as drawing this, but this is my y equals f of x. And y equals f of x is defined between this value of a and this value of b right now. If we look at this graph, I think you guys would all agree with me that we would say that between a and b, f of x would be continuous. So I could say that this graph is continuous. I'm going to abbreviate CONT on the interval between a and b. If you remember from last year, we don't use brackets when we name continuity intervals. It's just parentheses, and it's named according to the x-axis. So this graph would be continuous between the interval of a to b. I'm going to draw you another graph over here, which is going to be a little bit more complicated looking. Whoops, my pen went off. A little bit more complicated looking. Again, though, positive x and y axis. And this graph is going to have a couple different components. So it's going to come down, have an open dot, and then a closed dot. Then we'll have an open dot here, curl up, another open dot with a closed dot here, and then it's going to continue on kind of in this manner. So draw something that resembles that. I'm going to put some boundaries on this, and A is going to be about here on the x-axis, and B is going to be about here on the x-axis. And I'm going to name 3 points on the graph. We're going to have, let me choose another color here even. We're going to have point C sub 1. Oops, went off again. We're going to have point C sub 1, which is going to come down to about here. We're going to have point C sub 2, which is going to come to about here. And we're going to have point C sub 3, which is going to come to about here. I want to talk about the continuity at each of those points C sub 1, C sub 2, and C sub 3 between the interval of A and B. So we're going to make a couple notes about what's going on here. The first is the following. At C sub 1, so at C sub 1, what can you tell me about the function y equals f of x in general? Remember, this is y equals f of x. At C sub 1, would you agree if I wrote f of C sub 1 is not defined? Now, I'm writing that because when I go to C sub 1 and I go up to the y-axis, there's this open dot that would correspond to my y-coordinate. For the x value of C sub 1, I don't have a y-coordinate in existence. So we would say that the function at C sub 1 is not defined. Next, we're going to look at C sub 2. At C sub 2, sorry for the horrible writing, we would say this, that the limit as x approaches C sub 2 does not exist. Based on what we just studied in the previous section, we can assess the fact that when the limit comes from the negative direction towards C sub 2 and the limit comes from the positive direction towards C sub 2, they both approach different values on the y-axis. So we would conclude overall that the limit doesn't exist. At C sub 3, I would draw this conclusion, that f of C sub 3 does not equal the limit as x approaches C sub 3 of that function f of x. And I can say that because my function value at C sub 3 would correspond to a y value over here. My limit value, as it comes from the negative side and the positive side, our limit does exist because it approaches the same number, but that's going to equal some other range value over here. So we would say that f of C sub 3 does not equal the limit as x approaches C sub 3. The reason why I'm going through these three different pieces with you is that each of these has to be the same value if a function is continuous at a certain point C. And the first part is an example where the function doesn't even exist. So there's no way that our graph could be continuous. If our limit doesn't exist at a value in question on the domain, then our function also wouldn't be continuous because there would be this gap in here. And finally, if our function value doesn't equal the limit value, our function can't possibly be continuous at the domain value in question because those points aren't equal to each other. In order to make a function continuous, we would have to take the function value and have it actually equal the limit value. This hole would have to go up and plug that open dot right there in order for there to be continuity. So this we're going to define in a second a little bit more formally as the actual formal definition of continuity. Let me know if you have any questions on that graph. It seems like it makes sense, but again, you guys may have something that you have to ask me about when I see you next. I'm going to move to the next slide so that you can get what we consider to be this formal definition. Oops, sorry. This formal definition into your notebook. This is what I want you to write. The formal definition of continuity, which I can't get straight here. Won't stay. The formal definition of continuity is defined as this. Let C be a number in the interval between A and B. And so we have this value C. And let f be a function whose domain contains A to B. The function is continuous. The function is continuous at the point C if and only if, remember that's what that IFF means, these three criteria are met. 1 is f of C is defined. 2 is the limit as x approaches C of f of x exists. And 3 is that the limit value that you found in number 2 has to equal the function value that you're finding in number 1. So this value in number 2, our answer, has to equal the function value, which we found as our answer in number 1. If those two are not equal to each other, then we would say that there's a point of discontinuity at the value of c, or that the function would be would not have a point of continuity at that value in question. So this is a kind of an overall blanket statement. If f of x is continuous at every point in a and b, then it's continuous on the interval from a to b. That's how we state our answer. We use that word on, and we used it last year, so that shouldn't really be anything new, just a little bit more formalized. So as we move to the next slide, I have 2 theorems that you can use as we work through this. The first states the following. Every polynomial function, and we talked about what a polynomial function was in the limit section and reviewed that. Every single function that's considered to be polynomial is always continuous from negative infinity to positive infinity. If you can recognize that you have a polynomial function, then you can automatically tell me that its interval of continuity is negative infinity to positive infinity. There would be no breaks in that graph at all. On the other hand, if you have a rational function, those are the functions that have variables in the denominator, the ones that we studied a lot last year. Every rational function is continuous on every number in its domain. So if you can identify its domain, that's before you're factoring and reducing, then you should be able to identify the interval of continuity. Now, one thing that we're going to do that we did last year also is to identify the type of discontinuity we would have. So as I go through the examples with you, we're going to also put those types of classifications on things. Our theorems are going to be able to be used in order to prove continuity or discontinuity for many of our problems. There's going to be a specific time when we need to go through and use that formal definition. So let me get to, sorry that this keeps jumping around, to the examples that I want us to go through. The first is this, and the directions are reading, discuss the continuity. So I want to know the continuity interval of the functions that I give you. I want you to, if there is a point of discontinuity, identify what that point would be and classify the discontinuity as, these are our terms from last year, removable, non-removable jump, or non-removable infinite. Now the removable discontinuity was the one where we had a hole. The non-removable jump was the asymptote. I'm going to go off the screen, sorry. Stylus doesn't work very well for me. And the non-removable, no, I misspoke. You guys are probably saying, what is she talking about? Let me just pull out the eraser for a sec. I want to erase this. I misspoke here. I apologize. The non-removable jump is the type of discontinuity that comes from the piecewise. And the non-removable infinite is the one with the asymptote. So we will look at that and deal with that as we go through each of these problems. So the first one is the function f of x equals x squared minus 2x plus 3. We have 2 theorems that we can work with, and we have a formal definition. So if our function fits the criteria of one of those 2 theorems, we can get away with identifying the interval of continuity just by that. So f of x equals x squared minus 2x plus 3 is considered to be a polynomial function. And because it's polynomial, I can state that this will be continuous on the interval between negative infinity and positive infinity. So what that's implying is that there are never any breaks or gaps in that graph along the x-axis, because that's our continuity, the way that our continuity intervals are named. And I don't have to do any more than that, because I've identified through the theorem that this is polynomial, not through the theorem, but identified as polynomial and then applied the idea of the theorem. Now the function f of x equals x squared minus 1 over x minus 1. This is considered to be rational. This is like a lot of the functions that we studied last year. And in order to figure out what the interval of continuity is, we have to identify the domain. And we know here that x can't be equal to 1. If x were equal to 1, then that would make our denominator 0. So the interval of continuity is going to be from negative infinity up to that value of 1, union the value of 1 up to infinity. Now, the discontinuity, it's discontinuous at that value x equals 1. If I ask you to write where it's discontinuous, this is how you would do it. You would tell me it's discontinuous at the specific value c that we're concerned about. And you would tell me, does anyone remember what kind of discontinuity this is? If we look closer at this function, x minus 1 is actually going to factor out with one of the factors in the numerator, because that factors into x minus 1, that quantity multiplied by the quantity of x plus 1. And when those go out, it leaves us with that gap, which is just a hole. So this is a removable discontinuity. The hole would actually exist at the value of x equals 1, comma, 2. And if you have any questions about where that came from, we did talk about that last year. We can cover that again together when I see you next time in class. So two different types which actually fall right under the two theorems that we had, one polynomial and one rational. We're going to do a few more, so I'm going to move to the next slide. This next one is the function f of x equals x squared minus 2x minus 3 over the quantity of x squared plus 4x plus 3. So this is another rational function. And in order to work with this, I need to identify its domain so I can exclude the specific values that would make the denominator equal to 0. So I'm going to go through and I'm going to factor this. I'm going to factor this into the quantity of x minus 3 multiplied by the quantity of x minus 1 over, no, x plus 1, sorry, over the quantity of x plus 3 multiplied by the quantity of x plus 1. So looking at this before I do any factoring or reducing, that's where the domain comes from. That's where the interval of continuity comes from. I'm going to say that this function is continuous on the interval between negative infinity. Now the first gap is going to occur where this factor is equal to 0 at negative 3. It's going to pick up again and go from negative 3 up to where this factor is equal to 0, negative 1. Remember, I do this numerically as I go up the number line. Union negative 1 up to infinity. So this is my continuity interval. I would also say that this function is discontinuous. Keep forgetting the C. At x equals negative 3 and negative 1. Now the types of discontinuities, the discontinuity that occurs at negative 3 actually can't get reduced out, because my factors that get reduced out is the factor of x plus 1. So this is going to be a non-removable, and because it leaves us with x plus 3 in the denominator, that's going to be an asymptote, so it will be infinite. At x equals negative 1, that factor gets removed, so we would call it just removable. So your job is to be able to do things like this. Tell me the interval of continuity, tell me where the discontinuities exist, and classify any discontinuities that we might have. Now, again, pretty straightforward. This time, though, we had two different discontinuities that had two different classifications, so we just had to be careful with that. The final problem that I have for you is going to be the only problem that we have where we actually have to apply this formal definition of continuity. This is coming from a piecewise function, so we have our two-layered function. One layer is 5 minus x, and that happens when x falls between negative 1 and 2. And the other layer is x squared minus 1, and that occurs between 2 and 3 inclusive. The negative 1 to positive 2 for the upper part of the function is both inclusive. So we need to figure out the interval of continuity for this function. And if I look at each individual layer itself, let me just erase this here. If we look at each individual layer itself, both layers, the 5 minus x and the x squared minus 1 themselves, without putting these together as a piecewise function, are considered to be polynomial functions. So each layer by themselves is considered to be continuous on the interval for its for whatever it's defined for. So that means 5 minus x would be continuous between negative 1 and 2, and x squared minus 1 would be continuous between 2 and 3. The 2 is inclusive for this one, but it's exclusive for this one because the equal bar doesn't exist there. So the point in question between this entire domain that this function exists for would be at the x value of 2. If something's happening with its continuity, it's going to occur where the break is in the domain. So we've got a test. We're going to do what's called test for the continuity at that value where the break occurs, at x equals 2. This 2 is that c value that we used in that formal definition. So I have to, for every piecewise function, I have to go through this 3-part test. So the first thing I do is the following. I show on my paper, and I write this all out, I'm looking to define f of 2. Now f of 2 is defined for this function from the top layer because that's where 2 is equal. So I would, by substitution, show that 5 minus 2 is equal to 3. So f of 2 is defined. That's the first step in this process. Figure out if it's defined or not. If it's defined, then there's a chance that this function is continuous at x equals 2. If it's not defined, we would automatically know that there's a gap there and we can stop the rest of the proof. And we would be able to make a determination that it was discontinuous at 2. But because the function exists and it's equal to 3, we still have a chance that this is continuous. Step number 2 is this. Figure out the limit as x approaches 2 of f of x. Now, with every step function, we know that we need 2 different scenarios. We need to look at the limit as x approaches 2 from the positive direction, and the limit as x approaches 2 from the negative direction. Oops, that's a negative sign. So we have to figure out which of our layers is the positive direction, which of our layers is the negative direction. Now, values that are coming from the negative direction would be smaller than the value in question. So that's going to be our top layer. So 5 minus x will go down here. And that means x squared minus 1 will go up here with the coming from the positive direction. To assess the limit of a function that's polynomial, remember each layer is polynomial itself, we use substitution. So 2 squared, that's an equals, not a does not equals, minus 1 is equal to 3. And here we're going to say 5 minus 1, or minus 2 rather, is equal to 3. Remember, because these two are equal to each other, the limit from each direction is equal to each other, we can say overall that the limit is going to be equal to 3. So far we've proven that the function is defined. We've proven that the function has a limit. And step number 3, I'm going to do this one in a different color because it's a pretty important step, is to figure out whether f of 2, the value that we get in step 1, equals the value that we get in step 2, which is the limit as x approaches 2 of our function. If this value equals this value, which both in this case equal 3, then we can say, because that happens, therefore f of x is continuous on the domain that this function exists for. And for this function, the domain goes between -1 up to +3. So there are actually no breaks in this graph at all in this domain. The point that we thought there might be one was at 2, but we just proved algebraically that there's no gap at all because the function value actually equaled the limit value. If either number 1 or number 2 didn't exist, we would have a break in continuity, or if the value in number 1 did not equal the value in number 2, we would have a break in continuity. For example, if this turned out to be 3 and this turned out to be 5, then we would say that those two don't equal each other and that the function would be discontinuous at 2 or continuous from -1 up to 2, union 2 to 3. This is considered to be, that would be, if we had a break, it would be considered to be a jump, non-removable jump discontinuity. So this type of example is probably the one that you've got to pay most attention to as far as what I'm going to expect for things like notation and actual full proof. Take your notes. I'm going to give you some practice problems to try in class. I don't expect perfection at this point in time, but I will take questions when I see you next. So thank you for listening, and I will see you in class next time.